So let's focus on another article, which is scalable training of L1 regularized log linear models that we use for re-ranking. And this article in 2007. But they used this article in 2005 of Charniak, and also this article is very interesting. So we present an algorithm, orthant-wise limited memory quasi-Newton, based on LBFGS that can efficiently optimize the L1 regularized. You know, L1 is like lasso. I have an article on lasso. It was 2 years ago. I used it for financial networks. I mean, predicting some indices in financial markets like S&P 500. And L2, it's very simple, but L1 is better in the sense that it can produce sparse results, which is real good. We can even use it for explainability, because you have few factors that are important instead of thousands or millions of variables, and you obtain them. And so this article proves that it converges to a global optimum parameter vector. So the objective, like always, we have a log probability and a regularizer, but our regularizer uses the first norm, L1 norm. And these things are really important if you have a discontinuous problem. Sometimes you don't have a normal derivative, so use these problems like when you have the directional derivative, but here it could have. It depends on how you are formulating. It could be continuous or discrete. Not discrete, non-differentiable. I mean, so quasi-Newton is like constructs a local quadratic. So we approximate a function like this, and the algorithm is if you have seen my lectures on optimization, so these are very elementary things. And so we just choose an orthant here. For example, pseudo gradient of f at xi is this symbol, the pseudo gradient of f. And you could choose this orthant, and then you can use constrained line search. If you've seen my lectures on line search and those things, then you can identify how you can obtain, for example, these parameters beta and gamma. And so the algorithm is like this. First you compute v, and then you compute the derivative, and then you update s and update y. So what is important for us is this, how we can use this for re-ranking linguistic parsers, which is the original goal of this playlist. So all of these are articles, as I said in the previous lecture, are inspired by the work of Collins in 2000. And so first we assume that we are given n best candidates of parsers. And then we have training examples for each sentence, xi, and then y is the gold standard parse of that sentence. And of course a feature mapping, which maps x and your parse to a vector of feature values. So we define a distribution over parsers for each sentence according to this familiar model, this log linear model. So our task is to minimize this objective function and this loss, and where the loss term is the negative conditional log likelihood. So if you look at the denominator, it's just the total number of parses are just k equal to 20 or maybe 50. You take the 50 best parse. And what is important for you is learning these parameters omega. We are learning that. After learning, then we have access to this probability. And they use this article, this algorithm of Charniak for coarse to fine and best parsing, in that they get great F scores. If you compare it, you see it's more than 90%.